So welcome everyone. It's a pleasure for me to introduce the two speakers of today. The first one is Hugo Parada from Grenoble. He will talk about global well-posedness of KdV equation, a star-shaped network, and stabilization of the system. So Hugo, thank you. Please.
Thank you. Hello everyone. First, I want to give the thanks of the organizer to give me the possibility and be here online. And as well say Alberto, I'm going to talk about the well-posed result for the KdV equation, which is posed on a star-shaped network, and then some stabilization results using saturated controls. This is a joint work with my thesis advisor, Emmanuel Crepot and Christophe Priot. Okay. So first, to understand the idea of the problem, we are going to study the KdV equation, which is this one equation. This is a equation of third order, and it has here a nonlinear term. Typically, this equation is used to model the propagation of long water waves in a channel. And we are going to study this equation on a star-shaped network. This is like the structure of the network. In all this edge branch will be satisfies a KdV equation. And here in this central node, there is some conditions some boundary condition that means the interconnection of the system. The system was first studied in the work of Caisamaris and Emmanuel Crepot, and they studied some controllability and stabilization issues of this problem. And then in this work, the controllability result was improved using less control. And recently, we submit a work studying the system using some feedback delayed terms. So the system that we are going to study is the following one, and as we say, is this here. You can see that we have a KdV equation. This is the nonlinear term of the KdV equation. Here we have this important condition that is a continuity condition that tells us that in the central node, all the functions have to be the same. This is the continuity condition. Here we have a boundary conditions involve the second order derivative, and also it has a nonlinear boundary term, and also Neumann and Dirichlet-Wright null conditions and the initial conditions. This condition, and that alpha is greater than this quantity, was introduced in order that when you make the computation of the energy of the system, the energy is not increasing, and as the same boundary conditions that were considered in the past works. So to understand the idea, I want to explain you briefly the functional setting of this problem. This space H1R will be the sublevel space S1, including the null Dirichlet-Wright condition. The space is this one H1E will be the Cartesian dot of this space. Okay, it's the extension to the network, including also the continuity condition, and also the classical space here L2 in the network. This space BT is like the classical space where we can prove the well-posed result for the KdV equation. This is continuous L2 H1. And also here we introduce this space YT, which is all the function BT, but also we have extra regularity in this space, which is important that we are like changing the order. Typically we put time space, but here we put space time. Okay. So I want to first talk about the well-posed results. I want to explain briefly some related results. This one is the well-posed result that we have at this time in the past work. This is the work of Caisamaris and Serpa, Moreno, and Crepot. And they were able to prove the following well-posed result. If we assume that the lengths are given, alpha satisfies this condition, then for all t positive, there exists a epsilon such that if the initial condition in L2 is small enough, then we have a unique solution in BT. Okay, and the main problem to derive a global in time well-posed is the action of the nonlinear boundary conditions that I showed you before. Also, I want to show you this result that is about this system that was studied in the work of Rosier on a wave maker study, and also in the work of Caicedo, where I studied this KdV equation with this boundary condition, which is quite similar to our boundary condition. I mean, there is some difference between the parameters on the sign, but in the heart is the quadratic nonlinearity. And we have this result for this system that given a t positive, there exists a small time such that if the initial data is in L2 and this control edge is in h minus 1 divided by 3 is bound, then the problem has a unique solution, continuous L2, L2H1, and also has the hidden regularity given in red here. That if you see is the same idea that we have in the spice YT. So the first main result of this work is the following global in time well-posted result. We have this theorem that tells us if you have the length alpha greater than this time positive, then for all initial condition in L2, we have a unique solution in BT. And moreover, for a small time, we have more regularity. We have the solution, sorry, is in YT star, and we have this bond. So this result generalizes the past result in the sense that we are not asking for a small initial condition. And the schema of the proof is the following one. We follow the words of Caicedo and Song to prove similar hidden regularity for a linear system. Then to pass to the nonlinear, we use a fixed point approach and then some estimate to pass to the global in time well-posed result. I want to show the sketch of the proof. Okay, we consider this linear system. Here we keep the nonlinear terms, and also we keep a linear term here. So we have this linear system, the control edge, and null initial condition. And to this system, we apply Laplace transform, and we obtain this ODE system. This is the definition of the Laplace transform. And which is important of this is that here you have an ODE, so you can write explicitly, quite explicitly, the solution of this ODE. And following the work of Ona, we can write the solution of the system as this, where this lambda is the solution of the characteristic equation associated to this part, and these coefficients are associated to the boundary conditions. To keep in mind, the coefficient will be given by this, and if you impose all the boundary conditions to the coefficient, you can see that the coefficients satisfy this system. For example, this is a boundary condition associated to the second derivative, the right Dirichlet null condition, right non-bound condition, the continuity condition, and the others. I mean, which is important that we can write this system as in a matrix form, as AN will be the matrix associated to this system by multiplied by Cn equal to the control edge A1, which is the first canonical vector of R3n. Also, we can see that the matrix associated to this linear system can be decomposed in block form, which is very nice. Here we have the matrix in a case of a network of n-1 branch. This matrix Bn, this will be this matrix. This matrix will be a matrix Cn, and the matrix Dn given there. Which is good of this is that you can see that the matrix Bn and Cn has a lot of zeros. So when we make some computations with this matrix, there is a lot of terms that will be canceled. Okay, now we are going to give a formula to compute this coefficient. I want to explain why in later minutes. So we define delta n, the determinant of the past matrix that I defined. And this delta n, 3n minus 1 plus d, will be the determinant of the matrix n, but we replace one column by 1, 0, 0, 0, 0, by this one. Basically, is to apply Cramer rules. If we apply Cramer rules, we can show that the coefficient that we are studying are given by this division multiplied by the control edge. And formally, if we take the inverse of the Laplace transform, we derive this formula for the UN, for the component solution. So why this is important? Because when we want to show some regularity of this solution, we have to put focus on the important terms in this integral. Will be the exponential there, the division will be important, and also the effect of the exponential of the lambdas. And in order to make some computation of this, we are going to use this notation, plus and minus, will be related to this chain of variable. And in this case, we calculate we can compute, the lambda, and we can see that this lambda given by this. And recalling again that the positive part, plus, is related to this chain of variable, and the negative part is the conjugate of the positive part, or UN can be right in this form, which is like the positive part and the negative part. So if you see here, to see what happened with the regularity of an estimate of this part, we only put focus on the positive part. You have to see what happened again with this exponential, this division, and also here we have the action of Ryuku. So in order to estimate UN, we are going to show some asymptotic properties of this division. In particular, this is a result that I want to prove, the asymptotic properties for the divisions. And that you have to keep in mind is that in all these asymptotic properties, we have here rho power minus 2, and this rho power minus 2 will be canceled, the effect of this rho. And also we have some exponential that will be canceled, the effect of this exponential. And we need also for technical part asymptotic property for the sum. This is the main part of the well-posed result. So the proof will be based on an induction argument of the number of the branch of the network. First, we take n equal 1. And in this case, the system was studied in the work of Caicedo and Son for L1 equal to 1. So following this idea, we can derive the following asymptotic properties that we are checked with the case n equal to 1. Now we suppose that the asymptotic property holds for a network of n-1 branch. And by the block decomposition, if you write this matrix En in this form, but important is that if you have this block decomposition, the determinant of En, which is given by this one, is given by the determinant of En minus 1, determinant of this part, which is good because here is actually the determinant of En minus 1, which is the past case. But here we have this matrix product, which is a inverse of n minus 1 matrix. But for that, you can see the following. If you take x1, x2, x3, the first three elements of the first column of this matrix, as Cn and Bn has a lot of zeros, when you make this computation, we only survive these three elements. So this computation is not a big matrix, it's only this matrix, which is very nice. And actually, you can see that these three elements, as this is the matrix of the past case, as the first three divisions of the past case. So we know some asymptotic properties for this one, and actually one asymptotic property for the sum. Using that and some properties of the determinant, we can derive that this determinant are given by this, where this matrix Fn is given there. And finally, the determinant delta n is equal to delta n minus 1 multiplied by this. So now we have to compute the determinant delta n3 n minus 1 plus j. If we recall, it's the determinant of this matrix, the same matrix, but we replace one column by this. We have some several cases, instead that you are moving this column. Here you are putting the column there, there, there. And for this determinant, we have the following property. The determinant of the case n is the determinant of the case n-1 multiplied by the determinant of the n. I hope to see that, again, using this block decomposition that we have, the delta n, 3n-1 plus g, is given by the determinant of this matrix that is actually the past case, multiplied by similar, again, the determinant of this. And again, to see what happened, we have to see with the first element of this matrix. But you can see easily, because this matrix has a column that is 1, 0, 0, 0, 0, that this is the first column of the matrix. And hence, in all cases, this product will be 0. So we can, that this is 0. And finally, we have this formula for the determinant that we are studying. Hence, with this lemma, we have that the division that we are studying in the case n is equal to the division in the case n-1 multiplied by this red part. And by the induction hypothesis, we can estimate this. And also we know explicitly these three quantities. So we can see that this division is asymptotically like a constant given there. And as this is like a constant, using the properties for the past case will be the properties in this case. But this only holds for n-1 because in the other case we have to put more focus. We cannot apply this, but for that you can use again the block decomposition for obtain the estimate in the case n equal to big N. With this we have the following proposition. I don't full show the proof, by the idea that if we are taking control in h power minus 1 divided by 3, we have that the solution of the linear part is in yt and is bound by this. The idea is that we define this En, which is actually the positive part, and when we calculate some norms of this using some Plancher-like results, we have this one, and as we say, this part will be cancelled, this exponential and this row, and at the final we can derive the norm of h in the space that we have. Then using some classical method, we can add here a source term and the initial condition, and we have these results: initial condition in L2, control in h power minus 1 divided by 3, f in L1, L2. We have a unique solution of this system in yt. Then to pass to the nonlinear system, we use the following two lemmas. The following one is this, that give us an estimate of the nonlinear term internal that we have. And here it is very important that we have time in two parts. And also this gives us an estimate in this norm of the nonlinear boundary condition. It also is important that we have a t. This is the very important part. We prove all the other part to prove this, because in the past work, this estimate, when we use the fixed point approach, don't have the time. So you are not able to take time small to the fixed point approach, only initial condition small. So with this, as you have the time in two parts, using this new regularity, you can prove the local in time well-posed for the nonlinear equation in this space. And if you do some estimates, classical for KdV, you can derive the global well-posed in BT. So what about the stabilization part? Okay, first, in this work of Perlam and Saluzzi, they show that the one single KdV equation is exponentially stable if the length don't belong to this set of critical lengths. Also, in these two works, if you are in a critical case, you can achieve the stabilization adding a localized damping. Then in this work, they study that saturate the same damping that in this work, you actually can have the exponential stability. And in this work, we study the stabilization of the KdV and the star-shaped network using some delayed internal terms. So our idea will be follows the case, this work where it studies saturation for single KV on KdV, and this work of the stabilization of KdV in a network to prove the stability of our equation using saturated internal controls. In particular, we are going to show only the observability inequality. As you have the observability inequality, you can derive the exponential stability classically. And we are to consider the following saturations that are the same that were studied there. This local saturation, and this saturation in norm L2. Okay, so when we put sat here, will be log or sat2, it's the same, the local or in L2 saturation. So we are going to consider the following system, which is the KdV equation here, and we add the saturation term. We have the same boundary conditions, and this damp term An are acting in all the branches. They are positive, but acting only in a localized subset. Okay, what is important of this is this saturation map satisfies good conditions. So for this system, using the results of the global well-posed of the past section, we have also global well-posed for this system. So we define the classical energy, the L2 norm, And we can prove that if you have a bound initial condition, you achieve the stabilization, but which is important that the rate of decay depends on how big is the initial condition. So as we say, the idea is to prove the observability inequality. And for that, you can see the following. Making some integration by parts by this equation, we can derive the following estimate. And we want to prove this observability inequality. And if you see the difference between 18 and ops, you can see that this is the bad term, because this 3 is equal to this 3. So it's enough estimate this bad term by the other ones, which is given this. So it's enough to prove the observability inequality, prove the following inequality. And for that, we follow the classical approach. We suppose that this is false. So we can find a sequence of initial conditioned bound that satisfy this. And to see this in a better way, we normalize the functions. We take lambda g, the norm of the associated sequence. A bg will be the sequence normalized. So the sequence normalized satisfies this system, and this limit condition is still like this. Okay. For this system, making some computations, you can see that the sequence is bound in L2H1. This nonlinear term is bound in L2L1. The saturation term is bound in L2L2. And we could see that with this, the derivative of Vn, which is given by this, is bound in L2 h power minus 2. So using a one-Leon lemma, you can deduce that this sequence is relatively compact in L2L2, and hence you can assume that it converts externally, so some function be in L2L2. And which is important is that this sequence is normalized, so always has norm 1, so the limit function also has norm 1. So when you have that the sequence converges, you get to see what happened with the limit. So you can check that the limit function satisfies that the norm is 1 in L2L2, and also a solution of the following system, where this lambda, recall that is the norm of the path sequence U. So lambda is always positive, and you have two cases. If lambda is equal to 0, the nonlinear internal term heap disappears, and you can see that B satisfies a linear equation. And as Bn is 0 in an open subset, you can use Holmgren's theorem to conclude that B is equal to 0. If lambda is strictly positive, in this case, you can use other unique continuation property for the nonlinear equation to derive that B is equal to 0. In any of these cases, we have a contradiction because B is 0 and the norm is 1. So with this, you derive the observability and hence the exponential stability for the system. So I want to explain you finally this result that is the same idea, but is inspired by the following. We know that for one KdV equation, we only have to add the dump term if you are in a critical case. But in our past result, we add the dump in all branch. So inspired by this, we define EC all the n such that Ln is critical. And EC star with the subset of EC where we remove one index. For example, if you have 7 critical lengths, EC star will have 6 of these 7. We're going to consider the following equation. Here, note that you have only the linear part of the KdV equation, and we add here with a saturation term, where the saturation acts only, are positive only in the set E star C, and in the other is 0. And in this case, we are able to prove the following global stabilization result. So if you have any initial condition, you can show that the solution of this system satisfies this decay rate exponential. The main difference to this is that here, as you don't have this internal term, you can prove this stabilization without imposing condition of the bound of the initial data. So this is the main result that they want to present you. Thanks for following. If you have some questions, please.
Okay. Thank you, Hugo, for this nice talk. So we have time for some question or comments. If someone has a question, can open the microphone or write in the chat. Well, I have a question, Hugo. In your problem, you are dealing with a star network, no? So the boundary condition in the center is like a transmission condition, no?
Yes.
Is only the Dirichlet, no? So
yes.
Is the natural transmission condition for this equation for the KdV, or is possible to consider another transmission condition?
Yeah, if you change this, you can you lose the star network. I mean, this is like the star. Also, for example, you can consider there is a lot of work including the tree. So we consider the third equation is like this, and this is sparse. So you can consider an equation posed in a minus L1 0. In 0, consider that this go to other part. You can change this, but you change the structure of the network. Actually, there is some work studying other equations that consider more general conditions. I mean, like loops, infinity lengths, and I mean, you can have that you want here, but you lose the structure. You have a different structure of the network.
But okay, but keeping the structure of this network, you say that this is the natural transmission condition.
If you consider a star, yes, but you can consider other ones, for example.
Okay. And
okay.
Another question in the Enrique, yeah?
Yes, just a general question. Do you have any, can you get any consequence of the stabilizability regarding controllability, approximate controllability? What can you say of this?
I mean, for this system, if you add this dump system, for example, you get the observability. So when you have the observability, you can prove the controllability. But I mean, the part is how many controls you have to add. For this system, without using this approach, they're using some only estimate, you can prove the stability without the stat. For, I mean, if you are a network of n branch, n-1 controls. So you can derive the controllability, but using this approach, you don't apply the optimal numbers of controls. Because this, when you add this term, you prove the stability using for n controls. And actually, there is a result for less controls.
Okay.
Another question, Hugo, in the stabilization, how depends, do you know how depends the rate mu on R?
Oh, it's not easy to obtain this because, oh, sorry. When you,
for the method, no? Oh.
Yeah, it's for the method because you prove by on a contradiction argument, so you don't have a good estimate of this, of the observability constant, and the mu depends of the observability constant. So you don't.
Okay, yeah.
For other works, for example, in a work that we study the layer stabilization, for estimate the mu, we use a Lyapunov approach, so we can estimate explicitly mu is not greater than this, but it's only with a lot of restriction. Here, it's not possible.
Okay, thank you. Well, very well. Thank you, Hugo. Another question or comments from the public?
I had a question. Can I ask?
Yes, please, Yvonne.
Thank you, Hugo, for your talk. Very nice. Hugo, if I understood well, your proof of well-posedness is in L2, yeah?
Yeah.
It's possible to drop it, to drop the regularity, I don't know, for lower spaces, I don't know, H-1 pair or something like that.
Yeah. Let me show you this one is if I paste the comment. So, for example, the idea of the work, I mean, this is like a general system, is based in this work of Bona. and they work with this S between 0 and 3.
Yeah.
And if you take S equal to 0, you obtain L2. And we take S equal to 0 to take L2, but you cannot take S using this method S equal negative, for example, to consider initial condition in less regular space. But there is other works that you can consider as negative. So maybe with this approach, using this Laplace transform, you cannot consider this, but maybe use another approach, yes. I believe, I'm not sure, but there is a work when we use some Fourier transform, and we can consider S greater than -1 divided by 4.
Okay. Okay. Thank you.
Okay. There is another question or comment? If not, okay. Thank you very much, Hugo, for the talk. Yeah, you can keep sharing. Thank you. So we pass this on to the next speaker. Luca, are you ready? Okay. So are you ready, Luca?
Sorry. Okay. Okay. Sorry. Yeah, I'm ready.
Okay. Thank you very much. So the next speaker is Luca Salusi from University of Bath. He will speak about matrix-oriented HJB method for the control of PDEs in a tree structure. So, Luca.
Okay, so thank you for the presentation, for the kind invitation. So, okay, as I told you, I'm Luca Salusi. I'm a research associate at the University of Bath, and I'm going to present a joint work with Gerard Kirsten, which is a PhD student at the University of Bologna, and Maurizio Falcone from Roma La Sapienza. Okay, so what I'm going to discuss is a new method to solve the Hamilton-Jacobi-Bellman for the control of PDEs based on a tree structure. I will explain better later, but then coupling with the model order reduction techniques, in particular matrix-oriented. So that's the outline of the talk. I will briefly introduce the dynamic programming principle and the Hamilton-Jacobi-Bellman equations, and then I will pass to describe the tree structure algorithm, presenting the algorithm, some error estimates, and some particular cases in which we can say something more about the tree structure. Then I will pass to the coupling of the tree structure algorithm with the model order reduction techniques. In particular, we start with the model reduction in vector form. I will pass to the model reduction in matrix form. And finally, we will see the coupling of the tree structure with this new technique called two-side POD dime. And finally, we show some numerical experiments. Let's start by the introduction. This is our framework. So we have a dynamical system. So we starting from an initial condition X at time T. And we are considering a control U, taking an admissible set, which usually is taken values in a compact set in Rm, and is measurable. And we introduce also a cost functional. The cost functional, we recognize the cost functional a running cost L and a final cost G. Okay, so given this setting, what we want to do is we want to minimize, so we want to consider the infimum among all the possible controls taken in this admissible set controls of the cost functional. And we define this as the value function. The value function, which is a function of X, initial condition, and T. It's time dependent since we are considering a finite horizon problem. Okay, so what we know about the value function is there is this nice principle, the dynamic programming principle, which states in practice that given an arbitrary time tau, we can split the dynamics. We can consider the integral from T up to capital to tau, and then we can compute the value function starting from the solution obtained starting from y tau, so the dynamics obtained at time tau. Thanks to this formula, we can derive the Hamilton-Jacobi-Bellman equation. So you can see that the Hamilton-Jacobi-Bellman equation is a first order, non-linear since there is a minimization over a compact set. And we are fixing the final condition at the final time. So Gx is the final cost. It's important to stress that the x, so the space variable, is living in Rd. So it's like it's the same dimension of the dynamical system, of the original dynamical system. And this dimension can be very high. So for instance, think on semi-discretization PDEs, as we will do later, as we will see later on. So it can reach like thousands. So it can reach easily a very huge dimension. So it's really important to solve this equation in a very high dimension. So this is our aim. Then given the value function, once of the Hamilton-Jacobi, we can recover the optimal control just computing the argmin of the right-hand side. So we compute the value function, we compute the gradient, and then we can compute the argmin. We compute the optimal control, and using it in the dynamical system, we obtain the optimal trajectory. And we can say that the final, the optimal control problem is solved, is complete. Okay, so this is the introduction. Now let's move to the tree-structure algorithm. So the tree-structure algorithm is the following. So as I told you, we are starting, our dynamical system is starting from initial condition X in RD. And this will form our first level T0 of the tree. So it's a node X. Now, let's think on the easiest framework. So a constant delta T, we have a time interval, we discretize with a constant delta T. We have a control set U compact, we discretize in a U discrete controls. And then starting from this X, we can just consider like an Euler scheme. And we plug, you see, these discrete controls, U1, U and U inside the F. So you see that we are computing the first, the second level T1, and this will be made. This will be made of n U sons. So we will X, the father, and then U sons. We are considering now Euler, but it can be extended to implicit schemes, to high order schemes. So it's just for the sake of simplicity. Okay, so this is the first step. You can understand how we can proceed. So given the previous level, given the time, given the previous level Tn minus 1, we can compute Tn just computing the NU sons for each node. And so I'm constructing exactly a tree. This is exactly a tree, but I'm exploring, so using discrete controls, I'm exploring the different, so the various position of the dynamics. And Tn, so will be composed by Nu to the power n sons. Okay, this is the first part of the tree structure. We are constructing the grid. Given the grid, so this tree will be our grid. Now we have to solve the Hamilton-Jacobi-Bellman. For the resolution of the Hamilton-Jacobi, we rely on the classical semi-Lagrange scheme, in which we impose the final condition, the final time. So I have the final level, the final condition, and then I can proceed backward. Given the value function at time Tn plus 1, I can compute the value function at time Tn on the level Tn. But what are the differences with the classical semi-Lagrange approach is that we are not using interpolation. So the semi-Lagrange approach is based on a grid. This node, if this point does not belong to the grid, and so it must operate with some interpolation operators, while our nodes also belong to the grid by construction. We constructed the tree exactly in this way. Moreover, we will see that so we are mitigating the cost of dimensionality. We can, without the application of model order reduction techniques, we can easily deal with the dimension much more bigger than 10. There is still a con. So there is still a dimensionality problem. You see it's a tree, given a U controls and capital N time steps, the tree is growing exponentially as NU to the power n, capital N. So as I told you, each level is a U to the power n, so the tree is growing exponentially, and this is a problem if we want to reduce the time steps. One possible solution, so one of the possible solutions is the pruning. So what does it mean? Let's think that we have constructed a new node, this zeta is a new node. Then we verify this, if this new node, we compare this node with the already constructed nodes. If it verifies the pruning rule, so if it's close to another node with a tolerance epsilon, a threshold epsilon, what we can do is just to erase this node, and we can consider its father to point to the already constructed node. you can see that in this way we are deleting a node, but all the subsequent tree. So we have a drastic reduction. If it is verified, we have a drastic reduction of the cardinality. And what can we say? This is the pruning. What can we say about the error estimates? So for the error estimates, we base our error estimates on a paper by Falcone and Giorgi, where under just the ellipsis continuity assumptions, they put order 1/2. In this paper, in this submitted paper, we are adding more hypotheses. So we are saying that L and G, which are the running cost and the final cost, must be semi-concave, and F must be C1. And finally, we can prove order C1. So we can reach the first order convergence. More importantly is that in the pruning case, so if we are considering the pruning, and if the tolerance, the epsilon, the threshold that I described before, scales like delta t squared, delta t is the time step, we can keep the first order convergence. So it's stating that, okay, you can prune if you are using this epsilon, but you keep the first order of convergence. So this is quite important if we want to preserve the order of convergence. This is the theoretical foundation of the tree structure. There are some particular cases in which we can say something more about the cardinality of the tree. For instance, let's think that we are considering monotone controls. So we are changing the admissible set as a set in which U must be monotone, like non-increasing or non-decreasing. In this case, we have this proposition. So given m discrete controls, so again, we have m discrete controls because we have a control set, we are discretizing the continuous control set in discrete control set, discrete controls. And n time steps, the cardinality of a tree is n to the power m. If you see, now it's reversed. Before, so previously was n to the power n, which is, so this is nice if we are using just few controls, so like 2, 3, you see that the tree is growing quadratically, cubically. So it's important, like if we want to have information about the system just with few controls. And the proof is basically this one. So with two controls, you can understand that if I'm considering an increasing control, if I'm using Umax, the maximum control, I need to keep using the same Umax, the maximum control. While if I use the lowest, I can use both. So we have this particular structure. Then by combinatorial computation, you reach this cardinality, this order of cardinality. So this is one possible case that we will see later. Another possible case is the bilinear system. So if we are considering a bilinear system where U is scalar multiplying the solution, we using as a simple discrete scheme. So we reach this discrete scheme. What one can say is that given two, okay, this we are considering like a bank control, given two discrete controls and n time steps, the cardinality is at most quadratically. So you see that the proof is quite is based on this fact that if we are considering like U1, UN, so you have to think that yn is the solution with the control U1, UN, and y tilde is the solution with the y tilde 1, y tilde n. If the sum of the discrete controls are the same, then the two solutions coincide. So what does it mean? That if I'm using -1 and 1 and 1 and -1, the opposite, we are so they coincide, and this and what does it mean? That we have a huge decrease. So you see that the cardinality of the tree is quadratically. So we have a very nice behavior of the cardinality of the tree. Also, in this case, we will see a numerical test in which we will use this proposition. So these are some particular cases that we will see later. Okay, so this was the tree structure. Now we can pass to the coupling of the tree structure with the model order reduction techniques. Our setting is the following. Let's think that we have a solution y in R. So we are considering PDE in R2 in the variable x, where we see that there is a linear part L and a nonlinear F. So this is a semilinear PDE. If we semi-discretize, so with your favorite method like finite differences, finite elements, finite volumes, we reach and we consider the vector form. So even if we are considering a grid in dimension 2, then what you can do is just reshape and consider a very huge vector. And then you reach this huge system of ODEs, where Y is living in Rn and the A is living in Rn times n, where n is the product of the two number of discretization nodes in the x and the y axis. So this is in the vector case. So we have this this system of ODEs. Given this system, I describe POD, so proper orthogonal decomposition. How it works? So we consider the snapshots. The snapshots are just the solution at given time instances of the dynamical system. So I fix some time instances, I construct a solution, and then I collect all these snapshots into a full matrix. You see this matrix is n, so the multiplication of the discretization nodes times the number of snapshots. And basically it's based on a singular value decomposition. I take this tall matrix, I compute the singular value decomposition, and then I truncate. So I will consider just the first P singular values, the leading P, because the singular values are sorted in a decreasing way. And I'm considering, so I will consider this as I will consider book P as the new matrix, as the new basis. Moreover, we have also an estimate on the error. So on the Frobenius norm, the difference of these two matrices is just the singular values, the first singular values that we are neglecting. And so thanks to this, we can construct some a posteriori estimator to see if the projection error stays below a certain tolerance. But you see there is a constant on this approach. So the storage, you see the storage and the CVD are made on vectors of length n. So we are computing everything on the full dimensional n. And we will see by the numerical test that we cannot deal with very high dimensional problem in this case. So let's pass to the matrix-based form. So in the matrix, we recall that the PDE, so we have exactly the same PDE, this one, but now we are computing in a matricial way. So now Y you see is a matrix in error nx times ny, and A and P are just the discretization of the operator in 1D. So if you think to the Laplacian, we are just A will be just the tridiagonal matrix. And F is the nonlinearity. So now we are considering again, and I will repeat, a matrix ODE. So given this matrix ODE, what we want to do is to, first of all, we say for simplicity that that nx and y are the same. Then we want to compute two bases, W left and W right. So the second dimension K1, K2, which is much smaller than n. And we want this answer. So we want to substitute this y with a y hat multiplying the basis of W left and W right on the left and the right. So y hat is living in K1 times K2. So which reasonable, so hopefully which will be much more less than n. So if we project this ODE with this basis, we reach this ODE, which is living in K1 times K2. A hat and B hat are just, can be computed offline, are just the the evaluation, so the multiplication of the basis on the left, on the right. The only problem is on the linearity. You see that the non-linearity, first we have to compute Boel y hat. So the non-linearity must be computed on the full dimensional problem. So we have to recover the full dimensional, we evaluate the non-linearity, and then we come back to the low dimensional problem. So this first process is called the POD, so two-side POD, while for the second problem we need the so-called DIME. It's a second procedure in which is similar to POD, but we try to approximate the non-linearity just to avoid a full dimensional computation. Okay, let's see how it works to cite POD time. So this is based on a work by Kirsten Simoncini, present on arXiv, and is organized in two phases. The first phase is the approximation of the metric snapshots. So again, we have our snapshots, the solution at given time instances. And what we do for each, so yj is a matrix, we are computing the sparse SVD for each matrix. And we truncate, so we fix a k, so we can consider to fix a k such that to, so this is chosen a priori, just to have an a priori estimate on the length of the vector that we want to store. So each snapshot is then approximated by a reduced singular value. So what we do is to collect the left singular vectors, the right singular vectors, and also on a vector we will store the singular values. So how we go on? So we compute a new snapshots. I will compute the singular value decomposition, but then we have to reorder and truncate. So you see, we order the singular values in just in such that we consider the first k singular values, and then we rearrange also the left and right singular vectors. So we will have also a vector times k. So every time we are neglecting the singular values, so the lowest singular values. This is just the first phase where we are dealing with the snapshots. Then we are doing this for j going from 1 up to the number of snapshots. The second phase is the orthogonalization and truncation. So given the value, so given the vector, the left vector and the right vector, singular vectors, we compute another SVD. And then again, we truncate, we say, if the singular, on the singular value decomposition, we can recognize a part which we can neglect, we can directly consider just VL and WR as our basis. So VL will live in n times k1, while WR will live in n times k2. And also in this case, we have a criterion. So given an arbitrary tolerance tau, which will be related to the projection error. So we check if the Frobenius norm of what we are neglecting divided by the Frobenius norm of the entire matrix stay below this tolerance matrix divided by the square root of the snapshots. So this is how two-side POD works, two-side POD. Then for POD two-side time, there is a similar approach. So you see the pro is that now we are storing and doing the SVD on the square root of the n, or capital N, on n, and we will see that we get a nice improvement. Okay, so this was two-side POD. Now let's see how to combine the three-structure algorithm with two-side POD time. So first of all, we have to compute the snapshots. In our case, we have a tree. So the snapshots will be just a rough tree. So we will consider like util like two control discrete controls. So a binary tree with a chosen delta t. We are constructing this tree, and we are putting inside this computer. So we are putting inside this machine of the two-side POD time. We are fixing it at tolerance tau. We are considering all the snapshots given by the tree, and then by the procedure that I described previously, we can construct the left, and the right basis. And now we have to construct. So thanks to this new basis, we can consider the projected dynamics I showed you before, and we have to construct a new tree, which will be the tree reduced or projected. And we can consider or a smaller delta t or a final control space, so we can add more discrete controls. And then we proceed as without model order reduction. So we construct a tree and then we compute the value function on this tree. More about the error estimates. So first of all, we want to know something about the projection. So let's think that we constructed the left and right basis of the two-side POD approach. And now we have this snapshots set that is given from 1 up to NS. All these estimates, so for all these estimates, we are just vectorizing. So given the matrix, we are vectorizing, just doing the reshape. And we define the projection error as YJ, the vectorized snapshots, minus. So we are doing the Kronecker product of the basis because we are just using the vectorized form. This is the projection error, and what we can be shown is the following. So the projection error, we have this upper bound. We see that it depends on K1, K2, which are the dimensions of the basis, on the number of snapshots, on the Frobenius norm. The most important thing is that it depends on the singular left and right singular values in the second phase, and on the singular values neglecting on the first phase. So if all these singular values are going to 0 or are or can be bounded by a very low tolerance, so we have that the projection error is very low. So this means that everything is related to the singular values that we are neglecting in the two phases. So given this, we want now to provide some error estimates on the value function. So first of all, we want to see if the full dimensional trajectory, so we consider the full dimensional trajectory and the low dimensional trajectory y hat. So again, vectorized, so we are considering VU as the Kronecker product. And what one can expect is just that this L2 norm is bounded by the projection error on the Y. So this is the projection error based on POD, while this is based on DIME. I didn't explain, but you have to change ERDF. So we are constructing new bases with non-linearity, and we cover a similar estimate. So you see that exactly. So the difference, so the error between the full dimensional trajectory and two-dimensional trajectory is bounded by the projection error. Thanks to this, what we can do is to finally consider the theorem. So if we consider the exact value function and the reduced, so this is the reduced value function computed on the reduced tree, computed on the reduced initial condition, we have this delta t, which is given by the previous theorem. So the same hypothesis of the theorem means semi-concavity, Lipschitz, FC1, the same hypothesis that I described before. R plus, so the ST, so plus the projection error. This estimate is not so, it's useful from a certain point of view because this constant CT is very large. It's depending on some exponential terms, on the norm of the matrices. We will see that it's not, so the difference between this, the right and the left hand side is not, so this is not so sharp, this estimate. Okay, so I can pass to the numerical test. Okay, so first of all, the bilinear control. So I was talking about bilinear control. So let's consider the transport equation. We are multiplying y times u. So this is our domain. This is the initial condition. The cost function is just delta norm of the solution plus gamma, the norm of the control. We want to apply two-side POD, so DIME is not used. So we don't have non-linearity in this case. So we start by a RF3. We construct a RF3 with -3, -1. And as I told you, in this case, the cardinality of the tree is quadratic. So it's very fast. The construction of this tree is very fast. Then we are constructing all the bases with the tolerance tau equal 10 to the power -4. Both for POD, then we are going to compare POD and two-side POD, and then we are fixing the time t equal 2, so the time step, gamma equal to 0.1. But then the most important thing is that you see that C1 is 0.5 while C2 is equal to 0. We are considering a 2D problem, but the transport is just in one dimension. So this is reflected on the number of basis functions. So you see, I will pass directly on this table. So these are the dimensions of the POD and the two-side POD basis, increasing the number of on one dimension grid points. So you see that the POD, okay, is using 7, 8, so it's like a vector, while the two-side POD is a matrix, but we see that the second entry is the double of the first entry. This is explained by the fact that one dimension is very more than the other, so we need more basis to explain the direction in which is varying more. For this reason, we have this this difference between these two numbers from the left and the right singular vectors. Here I show I show the CPU time for POD and two-side POD. So you see directly that there is a nice difference between the two. But the most important thing is that you see that we had to stop with POD because after 160, if I remember well, yeah, the storage, so the laptop could not store dimension 170 square, so it was out of memory for MATLAB. And while for two-side POD, we can go on and we can consider even larger number of grid points. On the other hand, so if we think that we have a nice behavior for this is the offline stage. So we are just constructing the basis for our algorithm. In the online phase, I would expect that since it's a vector in dimension 7, while the two-side POD is a matrix in 3 times 6, I would expect that the two-side POD will be a little bit slower. But it seems, so thanks to this, in this plot, you see that varying the discrete control, so from 2 up to 7, the cardinality of the tree in two-side POD is much lower than the POD. So it seems like that after the projection of two-side POD, we are projecting in a in some space in which the variance is lower. So we have much more possibilities to have the pruning criteria, so that the two points are close according to the tolerance. And this implies also that the online phase is faster for two-side POD. And then, okay, this is just the optimal trajectory for time equals 0, 0.5, and 1 with these parameters. Let me shortly go to the Allen-Kahn. So let's talk about a nonlinear PDE. So a reaction diffusion with bilinear. We are considering again a bilinear control, Neumann boundary conditions. So this system has an unstable equilibrium which is 0, and we want to reach the unstable equilibrium, while as 1 and -1 which are stable equilibria. The cost function is the same, is the same, so the two norm of the solution and gamma, the U square. We are fixing these parameters, and now we are considering monotone controls. So the control set will be chosen in such a way that we'll take values in -2, 0, it's not decreasing. So we start from -0, -2, and then we increase. We don't decrease. So what does it mean? As I told you, that given m discrete controls, we have that the growth of the cardinality is nt to the power m. Then in this example, we exaggerated, we consider like 600 in each direction with a very huge dimension of the grid. So it's not necessarily such a huge dimension, but just to show that we can deal with very high dimension. And this is the error bound, okay. This is the error bound that I showed you before. So I make epsilon y plus epsilon f. And this is the error on the value function between the full dimensional and the low dimensional. You see that there is a correlation, and moreover that the difference is not so big. So yeah, it's big, but not as big as the constant that we found in the error estimate. So for the error estimate, the constant should be the constant will grow very fast, in an exponential way. While on the right, you see the CPU time. So since the tree is growing cubically, also the CPU time we have a cubic fit here. So for 400 time steps, it took like 300 seconds to obtain a solution. To obtain the solution in the online phase. And finally, I show you the optimal trajectory for initial time equals 0.5, and time equals 1. So we are reaching, you see that we are reaching the unstable equilibrium. the zero level. Okay, conclusion. So what we have presented today is a structure to solve finite horizon optimal control problems. We introduce a pruning rule, which can solve sometimes the dimensionality problem. We prove the first order convergence for both the full and the prune tree. And finally, we coupled with the two-side POD time. And you saw that we obtain for sure a more efficient algorithm in the offline phase, since we are storing less vectors, and we are dealing with a lower dimension, but also sometimes in the online stage, since we have more reduction in the pruning. So the possible future direction could be theoretical results on the reduced tree cardinality. Is interesting to see why the tree prunes more in the two-side POD framework, and then some processing procedure if we want to enlarge the control set. Okay, so that's it. Thank you for the attention. These are some references.
Okay, thank you, Luca, for the talk. We have time for some question or comment. There is some questions from the public. I want to ask you about the error estimates. You say that it's sharp, or it's
not sharp? It's based on this one. So where I checked the numerical experiment was capital boost, so the full dimensional minus Bohr reduced. So this constant, so sometimes it's based on Grenoble lemma. Then if we are reducing the delta x, the norm of the matrix is growing very fast. And so this constant is very high, so it's not useful. But if you check, it's not so the difference between the error and the approximation and the projection error is not so far. So the constant is not given an exact idea of the bound
of the sharp bound.
Yeah.
Okay, thank you. There is a question of Alessandro.
Yes, hi Luca. A comment on the monotonicity of the control, which I think it's not so realistic, especially if you have perturbation. I mean, it's hard to expect that you have a monotone control.
No, but I'm talking about if you want to stress. So if you start your control problem saying, okay, I want a monotone control. There are some, I look at the literature, there are some economic control problems in which they want to consider monotone control, since they want to, they start with some, I don't know, they have some energies, and then they want to decrease the amount of energy. And this is based on maybe some, yeah, so you start saying, I want a monotone control. I'm not saying the optimal control for the problem is monotone. So it's different.
Okay. And I have another, how do you solve the matrix equation in the, for instance, the Allen-Kahn equation?
Okay, it's based on I didn't, so there are some new works by Simoncini and Sgurra for the reaction diffusion, while for the transport there is another from always from Valeria Simoncini, in which they deal with the Lyapunov or the Sylvester equation, and they just decompose in a proper way to obtain like a very efficient algorithm. So it's based on some decomposition of the matrices in the Sylvester equation.
Okay.
Okay, thank you. There is another question or comments? No? If not, so thank you very much, Luca, and also thank you, Hugo, and all the people. So we stop here.